Welcome back, everyone. Today's deep dive is all about the Lorentz force. Specifically, how it affects a wire with a current running through it when it's in a magnetic field.
Sounds electrifying.
It is. You know, you're interested in physics simulations, right? Well,
Mhm.
we found an awesome interactive one for this topic.
Oh, cool.
Yeah, it was made by Francisco Escambra and customized by Lukong Wei. And it's hosted on the Open Educational Resources/Open Source Physics at Singapore website.
Yeah, that's a mouthful.
Right. It's quite a title. But anyway, the simulator is really cool because it lets us change a bunch of different things, like the magnetic field strength, how strong the current is, even the length of the wire and the angle it's at compared to the magnetic field.
I'm guessing the simulator shows us how all those changes affect how the wire moves.
You got it. The really cool part is that it shows how the wire can actually jump because of those forces. But before we get too ahead of ourselves, can we back up for a second and talk about what the Lorentz force actually is?
Of course. So basically, the Lorentz force is the force that acts on a charged particle, think like an electron, when it moves through a magnetic field.
So, like if we had an electron just zipping through a magnetic field, the Lorentz force would be the thing that pushes or pulls on it.
Exactly. And when we're talking about a wire that has an electric current flowing through it, it's actually the electrons inside the wire that are being affected by the magnetic field.
Makes sense. So all those electrons are feeling a Lorentz force, and that force then acts on the whole wire.
Precisely.
Okay, so now I'm curious. What are the things that decide how strong this force is, and also which way it's going to push or pull on the wire?
All right, well, first off, you have the strength of the magnetic field itself. A stronger magnetic field is going to mean a stronger force on the electrons and therefore on the wire.
So like a super strong magnet would make the wire jump more.
Exactly. And then another factor is the amount of current flowing through the wire.
Oh, so like if we crank up the current, the force gets stronger too.
Yep. More current means more electrons are moving, and that translates to a stronger force.
Gotcha. Okay, so stronger magnet, stronger current, stronger force. Anything else?
Yep. The length of the wire that's actually inside the magnetic field matters too.
So a longer wire means a stronger force?
Well, it depends. It's the length of the wire that's actually within the magnetic field that counts.
Ah, I see. So if only a little bit of the wire is in the field, the force is weaker. But if the whole wire is in there, then the force is stronger.
Exactly. You're getting it.
Okay, so we've got the strength of the magnet, the amount of current, and the length of the wire that's actually in the field. And I'm guessing the angle between the wire and the magnetic field also matters?
You're on a roll. Yeah, the angle is super important.
I figured. So like if the wire is straight up and down and the magnetic field is sideways, that would be a 90-degree angle, right?
Yep. And that's when the force is the strongest.
Right.
When the current and the magnetic field are perfectly perpendicular. Like you said, 90 degrees.
Okay, so 90 degrees equals strongest force. What happens when the angle changes?
Well, as the angle changes from that perfect 90-degree setup, the force starts to get weaker.
Huh, so it's all about that sweet spot at 90 degrees.
Pretty much.
Wow, this is already kind of complicated. Is there a way to figure out which way the wire will move with all these different factors going on? Like an easy way to visualize it?
Absolutely. There's something called Fleming's left-hand rule. It's a really handy tool for figuring out the direction of the force on the wire.
Fleming's left-hand rule. Sounds intriguing. What's that all about?
So you use your left hand, and each finger represents something different. Your thumb shows the direction of the force. Your index finger shows the direction of the magnetic field, and your middle finger shows the direction of the current.
Okay, so it's like you're pointing your fingers in different directions.
Yeah. And if you position your fingers correctly based on those directions, your thumb will then point in the direction that the force is acting on the wire.
So it's like a little cheat code to figure out which way the wire is going to go.
Exactly. It's a super helpful visual aid.
So how does this simulator we're talking about actually show all of this happening?
Well, that's the cool part. This simulator takes the idea of the Lorentz force and makes it come alive. You can literally see how the wire moves in real time.
Oh, wow. So we can actually see that jumping motion you were talking about.
Exactly. And you can play around with all those different factors we talked about. Like you can change the strength of the magnetic field or the current and see how it affects the wire's movement right then and there.
Sounds amazing. So we can actually test out all those different combinations and see what happens.
Yep. You can change the magnetic field strength, the current, even the angle of the wire. And the simulator will show you exactly how those changes affect how the wire moves and how strong the force is.
This is making a lot more sense now. Can we walk through some of the main features of the simulator, like how it actually works?
Sure. So one of the key features is that you can adjust the magnetic field strength and the current intensity directly.
So like we can just slide a bar or something to make the magnetic field stronger or weaker.
Exactly. And the simulator will show you visually how those changes affect the force acting on the wire.
That's awesome. So we can see those relationships in action. What about the angle between the current and the magnetic field? Can we mess with that too?
Oh, absolutely. You can change that angle. It's represented by the Greek letter theta. The one that looks like a zero with a line through it?
Oh, yeah, yeah, I know that one.
Right. So you can change that angle and see how it affects the force. You know how we were talking about how the force is strongest at 90
Right,
degrees?
right. When the current and the magnetic field are perpendicular.
Exactly. Well, the simulator lets you test that out and see it for yourself.
Awesome. So we can actually see that the force is strongest at 90 degrees, and then it gets weaker as we change the angle.
Yep, you got it.
So cool.
Mm.
What about this thing called the drag coefficient? It was mentioned in the source material. What's that all about?
Ah, yes. The drag coefficient. That's a fun one. It adds a bit more realism to the simulation.
Oh, how so?
Well, it basically simulates things like air resistance or friction acting on the wire.
Oh, I get it. So
Yeah.
in real life, the wire wouldn't just keep jumping forever, right? Air
Yeah.
would slow it down eventually.
Exactly. That's what the drag coefficient does. It lets you see how that resistance affects the wire's motion.
So it makes the whole thing more true to life.
Exactly.
Wow, this simulator sounds amazing. I can't wait to actually try it out.
I think you'll really like it. It does a fantastic job of showing how the Lorentz force works in a way that you can really see and understand.
This is already blowing my mind. And we haven't even gotten to the real-world applications yet.
Oh, there's so many cool applications. We'll get to those soon.
Can't wait. This is going to be good.
I'm excited to dive deeper.
Me too.
So we've seen that this Lorentz force is really important for understanding how a lot of our gadgets and motors work. But I think it's also important to zoom out a little and see how this force fits into the whole idea of electromagnetism.
Right. That's what's so cool about physics.
Yeah.
Everything seems to be connected somehow. So how does the Lorentz force tie into the bigger picture of electromagnetism?
Well, at its core, the Lorentz force is all about how electric and magnetic fields interact with each other.
So like they're not just separate things, they actually affect each other.
Exactly. It's not like they just exist independently. They're constantly influencing each other.
So it's more like they're in this constant conversation,
Mm.
and the Lorentz force is how they're talking to each other.
Yeah, that's a really good way to think about it. So when a charged particle, like an electron, is moving through a magnetic field, it actually creates its own magnetic field.
So like the electron becomes a tiny little magnet itself.
Exactly. And then that tiny magnetic field from the moving electron interacts with the bigger magnetic field from like a magnet. And that interaction is what creates a force on the electron, which is what we call the Lorentz force.
Okay, so it's all about those magnetic fields playing off of each other. But how does that force actually get transferred to the wire itself? Like, how do they make the wire move?
Well, remember that the electron is part of the current that's flowing through the wire. So when the electron experiences that force from the interacting magnetic fields, that force gets passed along to the wire, and that makes the wire move.
Wow. It's like there's this whole hidden dance going on between electric and magnetic fields.
Yeah.
And we only see the result, the wire moving, without really getting to see the actual forces at play.
It really shows you how something that seems simple on the surface can actually have some really deep and complex principles behind it.
This brings up something I've always wondered about. We talk about visualizing these fields through experiments, but can we really see them? Or are we just trusting that they're there, even though we can't actually see them?
It's true that we can't directly see these fields with our eyes, but we can design experiments that let us see their effects and understand how they behave. One classic example is the iron filings experiment.
Oh, yeah. I remember doing that in school.
Mm.
You sprinkle those tiny iron filings around a magnet, and they make these cool patterns that show the magnetic field.
Exactly. Those lines that you see are called magnetic field lines, and they show you the direction and strength of the magnetic field. So even though you can't see the field itself, you can see its influence on the iron filings.
I remember thinking it was magic when I was a kid.
Yeah.
But it's really just physics in action.
Exactly. And nowadays, computer simulations like the one we've been talking about can take this visualization to a whole new level. You can actually change different variables in the simulation and see how the fields change in response in real time.
It makes you wonder what other unseen forces might be all around us that we haven't figured out how to visualize yet.
That's one of the most exciting things about science. There's always more to discover. And as we keep learning more about these fundamental forces like electromagnetism, we'll be able to come up with even more ways to use their power.
Speaking of harnessing that power,
Mm.
can we talk about some of the real-world applications of the Lorentz force? You mentioned electric motors earlier, But you also hinted at some other cool examples. I'm curious to hear more about those.
Definitely. One that might surprise you is loudspeakers, the ones we use to listen to music and stuff.
Loudspeakers. Really? I never would have guessed that the Lorentz force has anything to do with how they work. How does that even work?
So think about it. A loudspeaker takes electrical signals and turns them into sound waves. And the Lorentz force is a key part of making that conversion happen. Inside a loudspeaker, there's a coil of wire called a race coil. And this coil sits inside a magnetic field that's created by a permanent magnet.
Okay, so it's kind of like the wire in the simulation. We've got a coil of wire inside a magnetic field. What happens next?
Well, when the electrical signal that carries the music or whatever sound it is, when that signal goes through the voice coil, it actually creates a changing magnetic field around the coil.
So the music is like making its own magnetic field.
In a way, yes. And that changing magnetic field then interacts with the magnetic field from the permanent magnet, and guess what happens next?
I bet the Lorentz force comes into play.
You got it. That interaction creates a force on the voice coil, the Lorentz force, and it makes the voice coil move.
So we've got the electrical signal turning into a magnetic field, which then messes with the other magnetic field, creating the Lorentz force. And that makes the voice coil move. But how does that create the sound that we hear?
Well, that force from the magnetic fields makes the voice coil vibrate, and those vibrations create pressure waves in the air, which travel to our ears, and our brains interpret them as sound.
Whoa. So it's like this whole chain reaction. The electrical signal gets transformed into a magnetic field, then that interacts with another magnetic field and creates the Lorentz force. Then that makes the voice coil vibrate, and those vibrations become the sound waves that we hear. It's amazing how it all comes together.
It really is. And all of that complicated stuff is happening inside the loudspeaker just so we can listen to our favorite tunes.
Mind-blowing. You also mentioned maglev trains, the ones that levitate using magnets. Now that really piqued my curiosity. Can you tell me more about how those work?
Oh yeah, maglev trains are super cool. They're a great example of how we can use the Lorentz force to create some really futuristic technology. Maglev trains use something called superconducting electromagnets, which are basically really, really strong magnets because they have almost no resistance to electricity.
Superconducting electromagnets. Sounds intense. Those are not your average fridge magnets, I'm guessing.
Nope, not even close. These magnets are super powerful, and they're placed strategically both on the train itself and on the track that the train follows.
So both the train and the track have these crazy strong magnets.
Yeah.
What happens when they get near each other?
Well, when those magnetic fields interact, they create forces, you guessed it, the Lorentz force, that do two things. First, they lift the train up a tiny bit so it's actually floating above the track. And second, they push the train forward.
Wait, so the train is literally floating above the track and moving forward, all because of the Lorentz force.
You got it. And because the train isn't actually touching the track, there's almost no friction, so it can go super fast, and it's a really smooth and quiet ride.
That's incredible. It's like something straight out of a science fiction movie. But it's real, and it's all thanks to understanding and using the Lorentz force.
Exactly. It just goes to show you how powerful these basic physics principles can be, and how we can use them to create some truly amazing technologies that can change the world.
This has been so eye-opening. We started with this seemingly simple idea of the Lorentz force, and now we're talking about things like loudspeakers and futuristic trains. It's amazing how it all connects together.
It really highlights how the things we learn in physics are actually all around us and playing a role in our daily lives. And it shows how important it is to keep exploring these fundamental principles to find new ways to use them and make cool new things.
I'm ready to go even deeper into this rabbit hole. What else is there to learn about the Lorentz force?
Well, there's always another layer to uncover, right? Let's talk about some of the challenges and limitations of actually using this force. Because even though it's led to all these amazing inventions, it's not always easy to work with.
So we've talked a lot about the Lorentz force and how it works, and we've seen how it's used in all sorts of cool things, like loudspeakers and maglev trains. But you mentioned that there are also some downsides or challenges to using it. I'm curious to hear more about that.
Yeah, there are definitely some things to consider when you're working with these kinds of forces. One of the biggest challenges is heat.
Heat. Oh, yeah. I remember learning that whenever electricity flows through a wire, some of the energy gets lost as heat.
Exactly. And that's because of the resistance of the wire. When the electrons are flowing through the wire, they bump into the atoms in the wire. And all that bumping and jostling creates friction, which generates heat.
So it's kind of like rubbing your hands together to warm them up.
Exactly. And that heat can be a big problem, especially when you're dealing with things like electric motors or powerful electronics. If the heat builds up too much, it can make things less efficient. It can even damage the components or create safety hazards.
Yikes. So it's kind of a trade-off. We get all this cool stuff from the Lorentz force, but we also have to deal with the heat it creates. How are engineers and scientists trying to solve this problem?
Well, there are a few different approaches. One way is to use materials for the wires that have lower resistance. So that reduces the amount of heat generated in the first place.
Makes sense. Less resistance, less heat.
Right. Another approach is to design better cooling systems so that the heat can be dissipated more effectively.
So like giving those components little fans or something.
Exactly. And researchers are also looking into new ways to control the flow of current more precisely. That way they can minimize the amount of energy that's lost as heat.
It sounds like there's a lot of work going into keeping things cool. What other challenges are there?
Another big challenge is the need for strong magnetic fields. Remember how we talked about how the strength of the magnetic field affects the strength of the Lorentz force?
Yeah. Stronger magnet, stronger force.
Well, for some applications like those maglev trains we were talking about, you need really strong magnets. And that often means using big heavy magnets, which can be a pain to work with.
Right. I bet those superconducting electromagnets aren't exactly easy to carry around.
Definitely not. They require a lot of specialized equipment and infrastructure. And just controlling those super strong magnetic fields is a challenge in itself.
Sounds complicated. Are there any other limitations we should be aware of?
Well, one thing to remember is that the direction of the Lorentz force is always perpendicular to both the direction of the current and the direction of the magnetic field. Remember Fleming's left-hand rule?
Oh, yeah. That was the thing with pointing our fingers in different directions.
Exactly. And that's really useful for creating rotational motion, like in a motor. But it can be a limitation if you need to exert a force in a different direction.
Yeah, I see that. So if you wanted to make something move straight up, but the Lorentz force wants to push it sideways, that would be a problem.
Exactly. So engineers have to get creative and come up with clever ways to work around that limitation. Sometimes they have to design special configurations of wires and magnets to make the force go in the direction they want.
It sounds like working with the Lorentz force is a bit like solving a puzzle. You have to figure out how to use its power while also working around its limitations.
That's a great way to put it. It requires a lot of understanding of the physics and a lot of ingenuity to make it work.
This whole conversation has been so fascinating. We started with this seemingly simple idea, and now we've gone so deep into all the different aspects of the Lorentz force. It's amazing how something that seems so basic can be so complex and have such a huge impact on our world.
I agree. It really shows you how powerful physics is and how it's all around us, even if we don't always realize it.
I'm already thinking about all the other things in the world that are probably using the Lorentz force without me even knowing it.
I bet there are tons, and that's what makes science so exciting. There's always more to discover and learn.
This deep dive has definitely given me a whole new perspective on the world. I'm starting to see things differently now.
That's great to hear, and hopefully it sparked a bit of curiosity in you to keep learning and exploring.
It definitely has. I can't wait to dive into another topic soon. Thanks for taking us on this journey.
You're welcome. It was a pleasure exploring this with you.